So now that we have a background in being able to predict electron configurations, we want to talk about what are some of the applications of that. And we're going to do that by looking at two things. We're going to talk about effective nuclear charge and how that relates back to the structure of where our electrons are within an atom, what orbitals they're occupying. And then we also want to connect that to this idea of ion charge. And we're going to look at the charge that an ion makes and its most stable charge that it would make. So any element has the ability to gain or lose electrons, but we want to talk about, will it favor losing electrons or will it favor gaining electrons, and how many? Is it going to gain 2 electrons to become a 2- charge? Is it going to lose 3 electrons to get to a +3 charge? We're going to go ahead and look at how we can apply electron configurations to kind of give us some insight into that. So first, the thing that we need to know is that when we're talking about the most stable ion charge formed for a cation, so a positive ion, or a negative ion, we're going to use this guiding principle, the octet rule. And before we do that, we want to see, do we know whether or not an ion is going to be positive or negative based upon the kind of element that we have? So our cations we will see are going to be our metals. So our metals are going to be the things that gain or lose electrons. Those could be our main group elements. Those could be our transition metals. It could be our post-transition metals, but we will see that these are the metals are going to lose electrons to make positive charges. Our non-metals, when they make ions, are going to be negatively charged. And we're going to see, well, how many will they gain or lose? And it's going to connect back to this idea of what we call the octet rule. So this is a guiding principle that we can follow that helps us understand what kinds of charges different elements may make. So the first thing we need to know is that atoms tend to gain or lose electrons, again, depending on whether they are metal or they are non-metal, in their valence shell. This is why we talked about valence electrons so much and why valence electrons are so important. And we think, why the valence shell? This is our outermost shell. It's the electrons furthest on average from the nucleus. They're going to gain or lose electrons until they achieve an outer shell that contains 8 electrons in the S and P subshells. So that's how many our S and P subshells can hold. They can hold 8 electrons total, 2 in the S and 6 in the P or electron subshell. In addition to that, we will also see that transition metals tend to be stable or have a lower energy when they have a completely filled or partially filled D subshell. And we'll see that this may contribute to types of charges that they make when they make ions. So let's go ahead and look at some application of this when we're looking at some electron configurations and predicting charges. So when we do this, we got to look at the element oxygen, and we got to figure out, is it a metal or a non-metal? And we notice that oxygen is a non-metal. And since we know it's going to be a nonmetal, it's going to gain electrons to become a negatively charged ion. And again, we can do that by looking at, we have that step ladder on the periodic table that has the elements that are kind of metalloids. They're in between a metal and a nonmetal. Anything to the top of the right of that are nonmetals. The majority of our elements are actually metals. So we look at oxygen and we see that it's going to be it's a nonmetal, and we've got to predict how many electrons it's going to gain to give it an octet. So we would write out 1s2, 2s2, 2p4 would be its neutral, just oxygen electron configuration. And we notice that we have 6 electrons in our valence shell, and that we need 2 more in the p subshell in order to give us a total of 8 electrons. So what we'll see, it's going to gain 2 electrons to give us 1s2, 2s2, 2p6, and that would be O2 minus. And we also see that that is the same as our neon electron configuration. So in this case, we reach that noble gas electron configuration. And again, that's a nonmetal gaining electrons, 2 of them, to give us a octet. Then we go to, let's go ahead and do bromine now. So let's go ahead and use our shorthand here, and we'd see that bromine is argon, 4s2, 3d10, 4p5, and we go here and we see it has 7 electrons in its valence shell, 5 in the p and 5 in the p and 2 in the 4s, and so we see it needs, that would be just for bromine, we need to gain 1 electron to give us Br minus, and that would give us now argon 4s2 3d10 4p6, which we could see is the same as krypton for our electron configuration. And so those were our nonmetals. Those are ones that gain electrons. So now let's go ahead and look at gallium. Gallium is a metal, and it's one of our post-transition metals. Again, this is just slightly to the right of our transition metals. And here, let's go ahead and write out our noble gas electron configuration. So it's argon 4s2 3d10 4p1. So again, a metal are going to lose electrons to get to where it has a valence shell that has 8 electrons in the S and P. And we notice here that this would have to gain 5 electrons to get all the way to 8 if it was going to make a negatively charged species. And this is why we notice metals would tend to gain a lot of electrons to need to be negatively charged, and nonmetals would have to lose a lot of electrons, too many, to get to a positively charged ion that has the same electron configuration as a noble gas, or 8 electrons in its valence shell. And so we see here, we notice that we have basically 2 sets of valence electrons. The higher energy 4p, but not as high as energy 4s. And again, reminding us, our 3d are not our valence electrons. Those ones are closer to the nucleus. These are not necessarily the ones we're going to gain or lose per se when we're just looking at our valence electrons here. So we see there's 2 sets, and we see we can lose 1 electron in the 4p. If I lose 1 electron here, we notice that we still have a full 4s subshell. But again, we haven't made it all the way to our octet. And so we'll see here is that gallium, this post-transition metal, is going to make 1 possible charge, which is gallium plus, where it lost that 4p electron, and it can also lose 2 more. So it can also lose 2 more in our 4s. So we notice that we have basically 2 sets of our valence electrons, 1 in the 4p and 2 in the 4s. And these transition metals and post-transition metals, we'll see are going to lose them in possible chunks, where we'll lose either all of the p orbital electrons and then all the s, or all of them. Okay, and we're always going to lose the higher energy ones first, which in this case would be the 4p electrons. And we lose 2 more, and that would give us gallium 3+, which is argon 3d10. And if we would go back and we see now we have in the 3 n equals 3 shell, we would have 3s2 3p6, and that's included in our argon electron configuration. So we see our gallium makes 2 possible charges here, and we were able to observe that by looking at our electron configurations that we would see for these. Now let's go ahead and look at our last one before I give you a chance to apply this on your own. Iron. Okay, iron is, if we look at the electron configuration of iron, it's argon 4s2 3d6. Okay, and we see here, we look at iron, and we notice that it has 2 valence electrons. So we would see here, and again, just to remind us, this is a transition metal, so it's a metal, it's going to lose electrons, and it's going to lose those 2 valence electrons in the 4s. As it loses those 2 valence electrons in the 4s, what we notice is that we get argon. Now we no longer have any 4s, so we have 3d6, and that would be iron 2+. We've lost those 2 electrons, so now it's a positive 2 charge. And then we go ahead and we remind ourselves a little bit about when we originally talked about electron configurations, that our transition metals like to have fully filled or partially filled, half-filled d subshells. And we'll see here, because even though our 3d electrons are not in our valence shell, we'll see that iron now has its most high energy electrons in this 3d subshell, and it has 6 of them. And we talked about originally electron configurations, 5 or 10 d orbital electrons is very stable or lower energy for our iron. So there's a trade-off here. We would actually want to lose this next electron, and we're going to lose 1 more electron, and that's going to be from that 3d6. Now, why is it going to lose that? Because it wants to get to a half-filled d subshell. And so we'd see here now we're going to have iron 3+, which is argon 3d5. And so we see here, if you've ever looked at iron and the charges that it makes a +2 charge and a +3 charge, based upon the fact that it can lose its valence electrons, the 4s, 2 of those, and then lose one in the 3d to give us a half-filled 3d subshell to give us 3d5, and that would be iron 3+. So these are the kind of thoughts that we want to think through in predicting ion charges. Metal or non-metal, gain or lose electrons. And then we're going to look at, from that, how many it's going to lose or how many it would gain to get to this octet. So now why don't you go ahead and take a chance to practice this on your own. So pause the video and then go ahead and write out what the predict the most stable charges would be for tin, silver, chlorine, and calcium. So now hopefully we've had a chance to be able to predict the relative ion charges that we would see for each of these. And we have tin, silver, chlorine, and calcium. Before we do anything, we always want to go into these and identify what kind of element they would be. Are they a metal or a non-metal? Because that lets us know that we are going to either lose or gain electrons based upon what kind of element that is. And then we go ahead and we look at the electron configuration of these, and we see we got tin here. Tin is a post-transition metal. Tin has 4 electrons in its valence shell, a set of 2 in the 5p, so we could lose those 2 to give us a tin 2+ charge. And then we got 2 more here. We could lose 2 more to give us a total of tin 4+ charge. And now we've gotten rid of all of our valence electrons in the s and p, and now our new valence shell would be the n = 4 shell, which is not shown here, but in krypton would have that full octet there. And again, we don't take anything from this d subshell because that d subshell is full. We're not going to want to take it away. It's stable in that d subshell. Then we go to silver. Silver, its electron configuration is that one of those weird ones where it's one of the electrons that would have been in the 5s orbital is actually in the 4d. And that one electron makes it so that it has a full d subshell. So it only has one valence electron. It loses that one valence electron, and it gives us a silver plus. And now again, we're left with this full 4d subshell where it's not going to want to lose any more electrons. Now we have chlorine. Chlorine is going to gain 1 electron because it has 7 valence shell electrons, so it wants to gain 1 more. When it does that, it gives us a Cl- or a -1 charge. And here we would see that that is the same, where we got 8 electrons total now in our valence shell. That's the same as argon, the noble gas. And then now finally we have calcium here. It's going to lose electrons because it's a metal. And we see it's got 2 valence shell electrons. It's going to lose those 2 valence shell electrons to give us calcium 2+. And now we have the argon. Same electron configuration as argon. So we'll see here, when we're gaining or losing these electrons, we need to look at our electron configuration, where those electrons are occupied, and then identify, based upon whether it's a non-metal or metal, what charge we would have. Now that we have this ability to kind of predict charges, one of the things we're going to talk about is why will a metal gain electron, a metal lose electrons, and why will non-metals gain electrons when they form ions. And the first step in us understanding this is talking about, well, what kinds of attractions will they feel if they are being lost or added to an atom. And before we can do anything that relates to that, we need to talk about effective nuclear charge. This is effectively what charge an electron would feel. We say that this is the Z sub F, so it's EFF, it's the effective charge of the nucleus, that an electron in the valence shell would effectively feel or experience in that valence shell from the nucleus. And let's talk about why would this differ from the actual charge of the nucleus, right? Z is what we classify as the charge of the nucleus. Why would it differ? Why wouldn't it be the same? And what we'll see here, one of the important things we're going to consider are core versus valence electrons. And our core electrons are electrons that are basically our non-valence electrons. Those are the closer to the nucleus. We call them core. And they are going to be typically more around the nucleus than our valence electrons. Our valence electrons a little bit further out. So we're going to talk about what is the effective nuclear charge that these valence electrons experience. Do they fully feel the full charge of a nucleus, or do they not? And for us to do this, we're going to first start with a simpler atom, beryllium. Beryllium, 1s2, 2s2. Okay, so that would mean if we were to draw this out kind of in an orbital diagram, we have 2 electrons in each of those s orbitals. Now we're going to say, okay, what are our valence electrons? Our valence electrons are these 2s electrons. And so now that we have these valence electrons, what we want to do is think about what kind of charge will they feel of the nucleus. Our beryllium has an actual charge of +4 because it has 4 protons. Okay. Well, are these valence electrons going to feel that +4 charge, or will it be slightly smaller? And let's talk about why that might be the case. So let's go ahead and we'll start with our +4 charged nucleus. And then we're just going to generalize, like our 1s, member is spherical, and it's going to be slightly smaller in shape of where those electrons typically are occupied. And so let's go ahead and draw in what we would typically find as our 1s orbital shape. Now reminding ourselves that we have these 2 electrons in here, and these electrons are always moving around. Okay, they're not stationary, but they're 95% of the time we're likely to find them within that volume that we've drawn. Remember that psi squared volume that we have. So again, we have those 2 electrons. They're closer to the nucleus, and then we would have also a little bit further away on average 2 electrons in the 2s subshell. Okay, and so what we see here is that we can think about it as these closer core electrons, right? These are our core electrons. Our 1s electrons are our core electrons, are going to be closer to the nucleus, and what they're going to do is they're going to act in a way where they're going to repel the outer electrons, and as they kind of repel those outer electrons, what they're going to do is they're going to reduce the charge that is felt by those closer, or those, valence electrons. So one important thing here is that our core electrons are going to repel the valence electrons. And what that does is that's going to effectively reduce the charge experienced by those valence electrons. And the way we classify that is they're going to shield the charge of the nucleus for those valence electrons. So we can think of it as blocking or shielding some of the charge that the nucleus would then project onto those valence electrons. So the valence electrons are going to experience less than that +4 charge. Now, how much is that? That amount, that effective amount, how much it's been shielded by, is what we call our effective nuclear charge. It's the charge that one of these valence electrons are going to effectively feel or experience for the nucleus. That's going to be our number of protons, or the charge of our nucleus, minus the number of core electrons. Okay, and so here, our effective nuclear charge, we'll see for beryllium is going to be, we have 4 protons. We got these 2 core electrons here, and that's going to give us a effective nuclear charge of +2. Now, what does that mean? That means that these valence electrons, what they're going to do is they will experience only a +2 charge from the nucleus instead of that full +4 charge. And we're going to see this is going to be important in us understanding how it's easier or more challenging for the electrons to be removed or added to these valence shells that we're going to look at. So again, we have the ability to see that there's this effective charge that our valence electrons feel based upon these core electrons kind of shielding or blocking the charge that they would feel. And then we're going to see there's going to be some applications for us on like how large our electron cloud is, the size of our atom, how easy it is, the ionization energy to remove an electron, how easy it is or hard it is to add an electron, what we call electron affinity. We're going to see a lot of that has to do with this idea of effective nuclear charge, and how that's going to correspond to the relationship between our core and valence electrons. So why don't you go ahead and kind of an application of this. Why don't you pause and practice and predict the effective nuclear charge for these 4 atoms. All right, so now that we've had a chance to predict this, let's go ahead and see and compare that to what I was able to think through. So our effective nuclear charge, again, number of protons minus our core electrons. Oxygen has 8 protons. There are only 2 core electrons, and so that would give us an effective nuclear charge of oxygen of +6. Bromine has 35 protons, atomic number 35. In all of these here, we would have 28 core electrons, and that would give us an effective nuclear charge of +7 for bromine. Gallium has 31 protons, atomic number 31. Again, all of our core electrons here, we have 28 of them. We would subtract those and we would get +3 for the effective nuclear charge for gallium. In iron, we have atomic number of 26 protons, minus all of our core electrons, which would be 24, and we would see that we have an effective nuclear charge of +2. So we're going to connect this in class to this idea of size, this idea of how hard or challenging it is to add or remove electrons to an atom, and then we're going to see that that's going to be one of the important things of us being able to predict electron configurations before we can actually follow through with effective nuclear charge or ion charges that we would see.